Okay, so let us get started. We have looked at the highest locker protocol, the priority ceiling protocol, the basic ideas priority ceiling protocol, the resource request and the resource release clauses. Now, let us look at an analysis. Let us try to analyze the priority ceiling protocol, its advantages, disadvantages, some examples, and before that let us we will look at example of how the priority ceiling protocol works. So, we will also try to establish these results, how deadlock is prevented here, how chain blocking is prevented, how unbounded priority inversion is prevented, and how inheritance related inversion is limited. So, first let us look at an example of working of the priority ceiling protocol. Let us take this resource R and CR1, and let us say R is requested by T1, T2, T3, R is used by T1, T2, T3, and T1's priority is 10, T2 is 2 and T3 is 5, and let us assume that the higher priority value indicates higher priorities, which is a window convention. Now, the ceiling priority of R will become 10 in that case, is not it? So, that is higher priority, highest priority among these three resources. Now, let us assume that a task T4 needs a resource CR1 and its priority is 8. Of course, we should consider only shared resources, right, and assume that CR1 is also shared by some other tasks. We have not shown that here because of lack of space here. Let us assume that CR1 is a shared critical resource. So, if it is exclusively needed by T4, then we do not have to consider that at all. Now, let us say T2 acquires the CR, T2's priority is 2. After acquiring the resource, the current system ceiling will be set to the ceiling of CR, which is 10 we have seen. And then let us say the task Tj, see here only the ceiling priority changed, T1 continued to have its priority as 2. Now, let us say T3 started executing because it has a higher priority 5, and after some time it needed CR. Okay, let us say priority of T3 is 3, I think it should have been 5 or something. So, 5, then by the inheritance clause T2 will become priority of T2 will T1 will become 5. I am sorry, this is T2, this should also have been T2, right. So, there is a mistake here. So, now let us say the task T4 starts executing and then requests the resource CR1, and then it will be checked against CSC, and because its priority is less than the CSC, T4 will block, and then T1's priority will increase to that of the T4's priority, because T4 is blocking on another resource. So, this will not be granted, request to CR1 will be rejected. Now, let us try to understand the different types of priority inversions that can occur under the priority ceiling protocol. Actually, there are 3 types of inversions that can occur. One is the direct inversion, then we also have inheritance related inversion. This we had seen in case of the highest locker protocol, and we had said that this minimizes inheritance related inversion, but does not eliminate it altogether. And then we will also have a avoidance related inversion. So, first let us see, let us try to understand what are these 3 types of inversion, and then we will do some analysis based on how much a task will undergo inversion due to all its resource requirements. First, let us look at the direct inversion, very simple, simplest of all possible, all these three inversions. So, here a lower priority task holding a shared resource and a higher priority task is waiting for the resource. So, directly the lower priority task is causing a inversion, priority inversion for the higher priority task. This is a direct inversion. I hope that there is no difficulty here. Just an example here, task scenarios. We have 6 tasks and there are 3 resources R1, R2, R3, and then these are the requests for different resources that can occur. T3 does not need any resource at all, T5 does not need any resource, and assume that the tasks have been sorted in order of their priority. So, T1 is the highest priority. We will not talk of priority 10 etc., because the convention, differing conventions. We will just assume that T1 has higher priority than T2, T2 has higher priority than T3 and so on. Of course, if the initial task set, the priorities were not ordered, we can just rename the tasks, so that finally we have got this task set T1 to T6 ordered in terms of their priorities. Now, these are the resource requirements. Now, what is the maximum or what is the direct inversions that T1 will suffer from? What is the direct priority inversion that T1 can suffer from? What are the inversions? Due to which task it will suffer a inversion? Yeah, T1 will suffer a inversion, priority inversion due to T2 on account of sharing resource R1, because it might so happen that T2 was holding the resource and T1 got blocked directly. Similar is the case with resource R2 required by 8, it could have been held by R4, T4. So, what is the maximum duration for which T2 can block T1 due to direct inversion? Yes, these are the millisecond values written here, 10 millisecond. Do you think that T1 will get blocked for 5 millisecond? 2 millisecond, because T2 can hold at best for 2, isn't it? After 2 it will release it. So, the maximum inversion to T1 caused by T2, maximum direct inversion is 2 millisecond. And what about R4? What is the R2? What is the maximum inversion due to its use of R2? 5. T4 can cause a direct priority inversion for up to 5 milliseconds. What about T2? What are the direct inversions it will suffer? Will it suffer a direct inversion due to T1? No, because that is not a priority inversion. T1 is already higher priority than T2. So, due to its resource use as R1, T2 will not suffer any direct priority inversion, and it will suffer priority inversion due to R3. And what is the duration? 8. So, it can suffer a priority inversion due to T6, the lowest priority task here, for up to 8 millisecond. What about T3? Will it suffer any direct priority inversion? No, it will not suffer any direct inversion. Okay. Now, let us look at the inheritance related inversion. When a low priority task is holding a resource and high priority task is waiting for some resource, then the priority of the low priority task is raised by the inheritance clause. Now, because the low priority task is executing at a higher priority, an intermediate priority task not needing any resource will undergo inheritance related inversion, because see it should have continued, because a low priority task is executing and this should have got preference over that. It is not able to execute just because that task priority has raised. So, let us look at an example. A low priority task was holding a critical resource and a high priority task is blocked directly, and by the inheritance clause this will acquire the priority of Th, the high priority task, and therefore, Ti would not be able to execute. It is not needing any resource, but it is prevented from being executed. So, that we will call as the inheritance related inversion. Now, let us take the same example. Tasks are sorted according to priority, these are the resource uses. So, what is the inheritance related inversion for T1? Will T1 suffer any inheritance related inversion? No, T1 will not suffer any inversion, is not it? Inheritance related inversion, because unless the inheritance clause is applied, and if the inheritance clause is applied to other tasks, then still it will be less than T1, is not it? So, T1 does not suffer a inheritance related inversion. What about T2? Will it suffer a inheritance related inversion? Yes. Okay. Due to what? Due to which task? Yes. It will undergo a inheritance related inversion due to T4. Assume that T4 is holding R2 and T1 is waiting for resource R2, then T4 the inheritance clause will be applied and its priority will become that equal to T1, and T2 will undergo an inheritance inversion. What about T3? Will it undergo inheritance related inversion? Due to which task? Yes, it will undergo inheritance related inversion due to both T4 and T6, because T4 priority might be raised to T1 due to the resource, and similarly T6 priority could have been raised to that of T2 because of R3. So, T3 will undergo inheritance related inversion due to both T4 and T6. Similarly, we can find for T4, is not it? What is the T6? Yes, exactly. What about T5? Due to T6, yes. What about T6? No, it is the lowest priority task, it cannot undergo any inversion. Now, let us look at the avoidance related inversion. Consider that a low priority task is holding a resource and CSC is made equal to the ceiling of the resources being held, and now a higher priority task whose priority is lower than the CSC, of course, it is larger than the task which is holding the resource, it needs a resource currently not in use. It should have been granted, is not it? Because it is requesting a resource which is not being used by the low priority task, and it has to wait because of the request resource request clause, where the CSC value is checked against the task priority and it will be denied the resource, and then we will say that the task that was denied the use of resource even though it was available. It is avoidance related inversion, occurs due to the resource grant rule. It is also called as priority ceiling related or the deadlock avoidance related inversion. Different terms used, but why is it called avoidance related inversion? Yeah, because this clause, this situation occurred because the task which was requested a resource not being used was not allocated just to prevent deadlocks. So, this is called as the deadlock avoidance inversion. This is an example of that. a low priority task holding resource CR1 and let us say the ceiling of CR1 is 10 and immediately after the low priority task acquired, its ceiling, the current system ceiling is set to the ceiling of the resource. Now, let us say another task whose priority is 8 started executing because its priority was more than TL, started executing, but after some time it requested CR2. Now, when it requested CR2, its priority 8 will be checked against 10. Now, assuming that 10 is a higher priority than 10, TH will be prevented from accessing CR2 and TH will undergo avoidance related inversion. So, what about this example? Will T1 undergo any avoidance related inversion? So, due to which it will undergo avoidance?
T2 is accessing R1 and if T1 has requested R2, it might get blocked.
See, for the CSC of R1, but ceiling
Okay.
of R1 is greater than
Right.
something.
Yeah. See, what he says is the situation is that T2 is holding R1 and the current system ceiling will be set to that equal to T1 and if T1 requests R2 first, see if it requests R1 then this is a direct inversion, but if it requests R2 first then it will not be granted just because the current system ceiling is already equal to the priority of T1, right. So, T1 will undergo avoidance inversion due to T2 holding R1. Is that okay? Now, what about T2? Will it undergo a avoidance inversion? So, due to which task will it undergo a avoidance inversion?
Holds R3 and if T2 requests R1, might
Exactly. So, R1 was available and T6 is holding R3. So, T1 will be prevented from getting R1 even though it was available and it will undergo avoidance inversion due to T6 for what duration? 8 millisecond, yes, because this can at best hold for 8 millisecond, but is there any other avoidance inversion for T2?
yeah, T4 holds R2.
Yeah. So, it will also suffer a avoidance inversion due to T4 because T4 gets R2, the current system ceiling is set equal to that of T1, T2 will be prevented and it will follow a avoidance inversion. But what about T3? Will it follow any, will it have any avoidance related inversion? Yeah, it will not have any avoidance related inversion because it does not require any resource at all. The avoidance inversion occurs when there is a resource request and already the CSC value is high. What about T4? Will it undergo a avoidance inversion? Yes, due to what? T6. Okay, T6 is holding R3, the CSC value has been set and it cannot access the resource that it needs even though it is available and it will undergo a avoidance inversion for what duration? 8, maximum 8 millisecond it can suffer avoidance inversion. Yeah, please. Yeah, right.
So, like in this case, like when T6 is accessing T6 and T2 is accessing R3, so the ceiling value of R3 is 2.
T6 and T6 is accessing R3, ceiling value is set to 2, that of T2.
So, like, and ceiling value for R2, resource R2 is 1.
Yes.
So sir, T4 therefore can't undergo avoidance-related inversion. So because the ceiling of R2 is greater than the CSC.
No. See, the way it works is that once T6 gets R3, the current system ceiling is set to T2. Now, if T4 requests R2, T4's priority is checked against the current system ceiling. So, current system ceiling is that T2 and T4's priority is less than T2, and therefore, it will be prevented from accessing R2. Is that okay? Clear for everybody. So, in the resource grant clause, the priority of a task does not change after getting a resource immediately, and the only thing that changes is the current system ceiling, and when there is a request made, the priority of the task is checked against the current system ceiling. Okay. Now, let us look at a theorem. The tasks are single blocking under priority ceiling protocol. Once a task acquires a resource, it cannot undergo any inversion. Just similar to the highest locker protocol, we will just give a scheme of the proof here, simple ideas, and which can be formalized. And the corollary will be that under priority ceiling protocol, a task can undergo at most one inversion. See, even though we talked of so many inversions, inheritance related inversion, direct inversion, avoidance inversion, but at best one task can undergo any one of those inversions. It cannot at the same time first suffer a inheritance inversion and then a avoidance inversion and then a direct inversion, not possible. So, this of course, this corollary will follow directly from here, because it is single blocking. So, once it has blocked under some inversion, it will not block further. So, that is the intuitive argument here, but first let us look at the theorem that tasks are single blocking. So, even though it requires multiple resources, it will block only once. Now, again like a previous one, let us take a example and then assume that in the more than one blocking will occur, and then so that such a situation will not exist. So, let us assume that a task, we have a resource R1 required by a task T1 and also required by a task T3. Let us assume T1's priority is 2 and T3's priority is, let us say, 10, and let us assume that 2 is priority 2 is more than 10, and let us assume R2, a resource again required by T3, priority of 10, and let us say we have another task T4 whose priority is 4. So, the ceiling value of R1 will be 2, is not it, assuming that 2 is a higher priority than 10, and for R2, so C1 is equal to 2, and for R2 C2 is equal to 4, right. Now, let us assume that T3 okay, I think T3 let us show it for T1 and then we need to show T1 also here, T1. So, the priority of the ceiling priority will become 2, T1's priority is 2, right. The ceiling C2 is equal to 2, the highest of these 3 priorities, right. Now, let us assume that T1 first blocked for R1 which was being held by T3, and then it blocked for R2 which was being held by T4. Let us consider that scenario and we will show that that scenario will not exist. So, T3 was first holding R1 and T3's priority does not change, only the CSC should have been set to 2, right. Now, T1, and let us assume that T3 sorry what we are saying T4, yeah. So, T4 started executing and it acquired the resource R2 and CSC will be set to 2, and then T1 first blocked for T3 direct inversion, and then after some time T3 released the resource R1, and then it found that R2 is already with T4, and then it again blocked for T4, but such a situation will not occur. Why is that? Anybody can argue why such a situation cannot occur? T3 is holding R1, T4 is holding R2, T1 first waited for T3, T3's priority increased due to inheritance clause, and then T1 waited for T4 to release R2. Why such a situation is not possible? Anybody would like to give any answer? So, first T3 has acquired R1, then T4 has acquired R2.
It's not possible because the CSC will not be T4 will not
Exactly, very good. Just look at his argument. He says that see T3 has got resource R1, CSC will be set to 2. Now, when T4 requests R2, its priority will be checked against CSC. So, it could not have been granted R2. Similar argument we can show if T4 first got R2 and T3 was trying to get R1. So, it is not possible. We can take all cases, I mean whatever example you can give, that T3 was holding both resources or any other example that you can think of, you can give, and we can show that such a situation will not be possible, and that we can just write formally saying that see these are the situations one task can hold both resources or they are held in two different tasks, and for each case we will show that it is not possible, and therefore, under the priority ceiling protocol the tasks are single blocking, and once it gets the resource it will not block for any other resource, they will be free by that time. So, it has the property of the highest locker protocol even without increasing the priority of the task to the ceiling value. So, the theorem that tasks are single blocking under PCP we can construct a formal proof based on the informal argument that we gave. We will just we can formalize that, that is what is done in the book. The same basic ideas are formalized, and the corollary of this is that a task can undergo at most one inversion. It cannot undergo two direct inversions, it cannot undergo one direct inversion and then followed by one avoidance related inversion, it is not possible. So, let us proceed with this. Next, let us argue why the priority ceiling protocol is deadlock free. So, the idea is that the deadlock can occur only when the different tasks hold parts of each other's required resource. So, one task is executing with some resource and part of its resource is being held by another resource, another task. But that we have already shown that if it is holding one resource, then other resources must be free, it is undergoing at most one blocking. So, by the theorem it is easy to show that it will be deadlock free. Now, what about unbounded priority inversion? A task could suffer unbounded priority inversion when it is waiting for a lower priority task to release the resource, and the intermediate priority task is preempting that task from the CPU uses, and the higher priority task keeps on waiting. But here that is not possible, because it would inherit the priority of the highest waiting priority task by the inheritance clause. So, the inheritance clause will prevent unbounded priority inversion. It is not possible that intermediate priority tasks would preempt the lower priority task from CPU uses, whereas the higher priority waiting task keeps on waiting. Now, what about chain blocking? I have already shown that it is single blocking, and if we say how chain blocking is avoided, then we will have to show how we argued that it is single blocking. So, to show that chain blocking does not exist, we will have to show that how the priority ceiling, the system ceiling was set, and how the priorities were compared of the task requesting resource, and that is why another task, two tasks cannot be holding two resources that are required by a task. The scenarios are not allowed under this protocol, right. Now, let us do some analysis. First, I will just do the analysis here on the slide, just observe it, and then I will give some example for you to work out. So, the tasks are ordered according to their priority, and these are their resource requirements, the time duration for which they need the resource, milliseconds. Now, let us find the direct inversion. Okay, I think there is a mistake here. So, T1 will undergo, I think it should have been T1, I have just written it by mistake. So, T1 undergoes direct inversion due to T2 for 2 millisecond, is not it, right? Okay, I know that is correct. So, I think I think I just interpreted the rows and columns differently. See here, these are the task names, and T1 suffers direct inversion due to which task? T2. Yeah, this is correct. Actually, I have done it okay, but I just got confused. So, T1 undergoes inversion due to T2 for 2 millisecond, direct inversion. Due to T3, it undergoes direct inversion for 8, and it does not need any other resource. So, it does not undergo any direct inversion with any other task. Now, what about T2? T2 needs only R1, so it will undergo direct inversion due to T3 for 8 millisecond, right, maximum. Now, what about T3? T3 needs two resources, R1 and R2, but T3 cannot undergo inversion due to R1 because these are higher priority tasks, right. So, T3 can undergo inversion due to T4, maximum for 1 millisecond. What about T4? It cannot undergo due to T3, but it can undergo inversion due to T6 for 8 millisecond, right, this 8 millisecond it can undergo. What about T5? T5 does not need any resource, so it cannot undergo any direct inversion, and T6 is the lowest priority task, it cannot undergo any type of inversion, not only the direct inversion. Now, what about the inheritance inversion? Okay, I do not have the diagram here. So, we have to, so just check here, what will be the inheritance inversion for T1? Nothing, T1 will not undergo inheritance inversion. What about T2?
The T2 is also not involved.
Will T2 undergo any inheritance inversion? No. What about T3?
So it will undergo.
It will not undergo any inversion, is it? Is it? Yes, please look at it. Will T3 undergo any inheritance inversion? It cannot undergo inheritance inversion because
The T2 can undergo inheritance-related inversion.
T2 due to
Sir, because like if T3 is holding it.
T3 is holding R2.
R1.
T3 is holding R1, then T2 will undergo a direct inversion.
No, sir, and T1 is waiting. See, T1 has come earlier. So, sir, the priority of T3 is now increased to T1.
Okay.
And now T2 has come. So then T2 has to wait.
So that's a so T2 so the T3 is holding R1 and T1 is waiting for T3, then T3's priority would have increased.
Yes, sir. So T1.
So that will be a avoidance inversion, isn't it? Okay, what about T4? Will it undergo inheritance inversion? Yes, will T4 undergo a inheritance related inversion? See, just look at the basic definition of inheritance related inversion. In an inheritance related inversion, a task is not progressing even though it does not need a resource, because the priority of the task that is holding the resource has increased. Okay, I think according to that definition, T2 will follow inheritance inversion, isn't it? See, what he says is that T2, let us say it is not needing R1 for some time, it is executing, and then because T3 is T3 is holding R1 and T1 is waiting for R1. So, T3's priority would be raised to that of T1, and T2, even though when it is not needing R1, it cannot execute, isn't it? So, T2 will undergo inheritance inversion, that is correct. Do you see the difference here? Inheritance inversion occurs when even when the task is not needing a resource, it is not being able to progress, because the task that is holding the resource, its priority has increased due to another higher priority task waiting. But in avoidance inversion, a task needing a resource not required by any other task is blocked because of the current system ceiling comparison rule. Is that okay? So, yes, T2 will undergo a inheritance inversion due to T3 for what duration? Okay, 8. Now, what about T3? Will it undergo inheritance inversion? No, it cannot undergo, because no other task can inherit another higher priority task. What about T5?
T5 will undergo inheritance inversion.
Yes. T5 will undergo inheritance related inversion due to which task? T6 naturally. Now, what about the avoidance related inversion? Which task will undergo avoidance related inversion? Will T1 undergo avoidance related inversion? Due to which task?
T2 is holding R1 and CSC of R1 will be equal to T1. T1
No, but T1 doesn't require any other task.
So, T1 will be directly blocked by T2, that we have said. So, will there be any avoidance related inversion? T3. So, T3 due to which task? T3 requires R2, yes.
But it is not granted as T1 or T2 is using R1.
No, you do not suffer inversion due to higher priority tasks. If a higher priority task is executing, it is not inversion. Inversion is that when a lower priority task is executing and this is prevented.
T4 I think.
Okay, let us see T4.
T6 is holding R3 and CSC of R3 is equal to T4, and then T4 requests R2, it cannot be granted because the CSC is equal to T4, it is not greater than T4.
Okay. Okay, so T4 will undergo a avoidance inversion.
T6 because CSC of
R3
is equal to
exactly, exactly. So T4 is holding, T6 is holding R3 and the CSC is set to the ceiling of R3, which is T4, and T4 started executing, and then after some time it requested R2. It is not greater than CSC. So, it will be prevented from using R2. So, that will result in a avoidance inversion, but what duration? 8. Okay.
So the same thing will hold for T3 also.
Yes. So what about T3?
So like T4 is holding R2.
T4. Yes.
CSC is set to 3, and then T3 can't access R1.
Yes. T3 cannot access R1. So T3 will also undergo avoidance related inversion due to R2 for 1 millisecond. So is the computation clear? So let's. So I have written those values here. So now one thing that we need to look at is that each of these matrix, we just did 3 tables. One is the direct inversion, the other is the avoidance inversion, and we did the inheritance inversion, 3 different tables. Now all the 3 tables will be upper triangular matrices. Why is that? You draw for any task set, you will find that the inversion tables, each of them are upper triangular matrices.
So they are sorted among the priorities.
Okay, so then why? Then sorted doesn't, I mean, why should it make it upper triangular?
That is logged only because of the lower priority.
Exactly, exactly. So the reason is that a task does not suffer any inversion due to higher priority tasks. So one part of the table will be empty. The lower priority with respect to a higher priority task will not undergo inversion. So that part will be empty. So only half of that some entries will be there.
Sir,
Yes.
could you please go back to that table? So like
This
for
one,
that
no?
avoidance, so we identified T3 and T4.
I have not written that here, but what we identified, is that clear? So we will take some example and then we will. So here I have not populated all this, we need to populate here. The avoidance related inversions here, we identified that T3 will undergo avoidance related inversion and T4 will undergo avoidance. So we need to populate that in the table. But one thing is that a task undergoes at most one of the inversions by our theorem. So the maximum inversion that a task can suffer, we can check the entries on all the 3 tables for a row and find what is the maximum value there, any of the entries in the 3 rows, and then pick that one.
This is the worst case.
Worst case, yes. We are trying to find the worst case, the maximum inversion that a task can occur, because all the scheduling, all analysis with respect to the worst case. Now let us do an exercise. So let us assume this is the situation, again 6 tasks arranged increasing order of their priority. So let us find the 3 types of inversions and then find the maximum inversion that a task can suffer. So, for first let us do the direct inversion. So, you tell me the values, I will write here the direct inversion table. So, we have the tasks T1, T2, T3, T4, T5, T6 and let us write T1, T2, T3, T4, T5, T6. Okay. First look at the diagram and then tell me what are the direct inversions, we will just populate on this table, right. Okay. So, yeah. So, we will just look at the diagram, yeah. So, what are the direct inversions for T1? T1 will undergo direct inversion due to which task and for what duration? Yeah, it will undergo direct inversion with T2 for what duration? 2 millisecond, yes, and also for T4 for 5 millisecond. Now, what about T2? Yes, T6 alone for 8 millisecond. What about T3? It will not undergo any direct inversion because it does not need any resource. What about T4?
No, sir.
It will also not undergo any inversion because if T1 is holding R2, then it is not an inversion because that is a higher priority. What about T5? It will also not undergo any inversion. What about T6? It will also not undergo any inversion because this is the lowest priority, all others are higher priority. So, let me just write down what you told me. So, T1 will undergo inversion due to T2 for 2 and for T4 for 5, and T2 will undergo due to T6 for 8 and T3 will not undergo any inversion. T4 will also not undergo any inversion, T5, T6 etc., none of them will undergo inversion. So, only T1 is undergoing inversion due to 2 tasks and T2 due to 1 task. So, let me just draw the line so that we do not get confused here. Now, let me just let us do the inheritance inversion. So, again look at the diagram and please tell me about the inheritance related inversion. So, again we will write T1, T2, T3, T4, T5, T6, T1, T2, T3, T4, T5, T6. So, now let us look at the diagram and then identify what are the inheritance inversions. I will populate on this table. So, the tasks what about T1, will it undergo inheritance inversion? So, inheritance inversion, just remember that the task that is holding the resource and there is a task waiting for the resource and the task holding the resource has inherited the priority of the waiting task, which is greater than the task that is we are considering, and then it is preventing it from being executed. So, what about T1, will there be an inheritance inversion?
Yes. Yes,
Due to which task?
can we do T2, T4?
No, see, we have to have a situation where a task is waiting for a task holding the resource whose priority, the waiting task's priority should be more than T1.
So T1 will not undergo.
T1 will not undergo any inversion because this is the highest priority task, right. Any other task that is waiting will be lower than T1. So, T1 cannot undergo inheritance inversion. What about T2?
T2 will undergo due to T4.
T2 will undergo due to T4. T4 is holding R2 and T1 is waiting, its priority is raised and T2 cannot execute. Yes, T2 will undergo inheritance inversion due to T4 for 5 millisecond, right. Now, what about T3?
It will not undergo. It will also undergo due to T4.
T3 will undergo due to T4
And
for
T6.
5 and T6 for 8. What about T4?
It will undergo due to T6.
T4 due to T6. What about T5?
Due to T6.
Yeah, T5 due to T6. Okay, let us just, whatever you said, let me just write here that T1 does not undergo any inversion and then T2 will undergo on account of T4 for 5 millisecond and T3 will undergo
T4
on account of T4
and T6.
for 5 millisecond and on account of T6 for 10 millisecond and T4
It will undergo due to T6.
will undergo due to T6 for 10 millisecond and
So
T5
T6.
will undergo due to T6 for 10 millisecond. So, this is the inheritance inversion table. Now, let us work out the avoidance inversion table. So, again let me just draw the table, avoidance inversion table, T1, T2, T3, T4, T5, T6, T1, T2, T3, T4, T5, T6. Okay, now let us look at the diagram and try to find the avoidance inversions. So, first let us look at T1. Will it undergo avoidance inversion? Yes, see, in avoidance inversion, remember that the CSC is set to a priority higher than, sorry, equal to or higher than the task and it cannot execute.
So T1 can undergo due to T4. Like if T4 is holding R2, so the CSC is set to 1.
Yes.
And then T1 cannot acquire
R1, exactly. So, T1 can undergo avoidance inversion due to T4 for 5.
Right. Then similarly for T1 can also acquire this thing for T2 because T1 is now holding R1. So the CSC of is set to 1 and then T1 cannot acquire R2.
No, no, sorry, what is the scenario?
So it can be both ways, no? So like
No, no, let us,
T4 is holding R2,
T4 is holding R2.
CSC is now set to 1. So that task T1 cannot acquire R1.
Okay,
Then suppose now T2 is holding R1, so the CSC
Okay.
is again set to 1.
right,
So
right.
then T1 cannot acquire R2.
Okay. So, what are the T1 undergoes in avoidance inversion due to which two tasks?
T2 and T4.
T2 and T4. So, that is for 2 and 5. What about T2?
The T2
What about due to T4?
No, it will not go.
Why not? See, T4 is holding R2, priority set to 1,
Yes, that time it will go.
and then T2 is needing R3
yes.
or R2, R1 or R3.
Yeah.
So, it will undergo 5 due to T4. What about T3? Will not undergo avoidance inversion because it does not need any resource. What about T4?
T4
T4 will undergo inversion due to T6, because T6 is holding R3 and T4 is prevented from locking R2. What about T5? T5 does not need any resource, it will. So, we can write those values here in the table. So, T1 does not undergo any avoidance inversion, and
due to T2 and T4.
okay, T1 undergoes due to T2 and T4, yes, right. T1 undergoes due to T2 and T4. So, for 2 and 5, and T2 undergoes on account of T4. So, for 5, T3 does not need any resource, does not go undergo any inversion. T4 undergoes on account of T6 for 8, and T5 does not need any resource, does not undergo any avoidance inversion. T6 lowest priority does not undergo any avoidance inversion. And then we find out the highest maximum inversion for each task. So, here avoidance inversion, the maximum value for T1 is 5, and if we look at the inheritance inversion, it does not undergo, T1 does not undergo any inheritance inversion. Look at the direct inversion, it is again 5. So, the maximum inversion for T1 is 5. T2 avoidance inversion is 5, inheritance inversion is 5, direct inversion is 8. So, it will maximum inversion it can undergo is 8. Similarly, T3 undergoes no inversion, no avoidance inversion, inheritance inversion 10. So, maximum inversion is 10. So, we can work out like that, and based on the maximum inversion, in the next class we will find out the total completion time, worst case completion time for a task, and see whether it will meet the schedule even when the tasks undergo the share resources, right. We will extend the Lehozki's clause, Lehozki's expression, and we will incorporate these values to check the schedulability criterion, right. We will stop here.